All right, our primary purpose then today is we're going to finish out chapter 5. And in finishing out that chapter, we're really going to focus on two big ideas. The first big idea is this idea of a half-life. And then the second idea is kind of some modern applications of nuclear chemistry. So how do we actually use the fact that some of these substances are radioactive to a more purposeful end rather than just avoiding them because they happen to be radioactive? So we'll start with half-life. Half-life is a useful tool for us for a couple of reasons, but to define half-life, what we need to do is we need to talk about what it is. When we describe the half-life of an isotope, we are talking about how long does it take for half of that isotope to undergo some kind of radioactive decay. So if I have a sample here of iodine 131, we've got 20 grams of it. We would say that one half-life has elapsed when that 20 milligrams of iodine 131 is 10 milligrams of iodine 131. And furthermore, we would say another half-life has elapsed when that 10 milligrams of iodine 131 turned into 5. And another one still when that 5 turned into 2.5. What's important for us to notice in this reaction is that the time that it takes for that process to occur does not change. In radioactive decays, these half-lives are the exact same length of time. Even though the amount of material is changing, even though the amount of material that ultimately reacts changes, the time itself is not going to change. So whatever the half-life is for iodine 131, that amount of time it took to do this first, that same amount of time it took to do the second, that same amount of time it took to do the third. Now, this is a unique phenomenon. Most chemical reactions behave in a different kind of way. I would say most, a number of them do. But for radioisotopes and for radioactive decay, they follow this very predictable pattern. And the nice part about that is because it is so predictable, we can actually use this concept to try to figure out how long things have been decaying. If we know how much was there at the beginning versus how much there is now. Graphically speaking, we can take this concept here and put it into a bar graph or a line graph. And what we would see is that as the reaction proceeds, it is getting slower as fewer material is present. So the graph here shows that half-life for the iodine 131 is about 8 days. So in the first 8 days, 10 milligrams of that sample decayed. In the second 8 days, 5 milligrams decayed. In the third, 2.5 milligrams. In the fourth, 1.25 milligrams. Each successive half-life took the same amount of time, but notice that each successive half-life decayed less and less and less material. So these kinds of decay functions do have a tendency to slow down as the amount of radioactive material present decreases. But from a half-life standpoint, the half-life is always a consistent value. Some common isotopes that we are interested in and their half-lives. Carbon-14. Carbon-14 is used in the technique of radiocarbon dating. Radiocarbon dating is used to pretty much any kind of sample that comes from living material. Radiocarbon dating is the most common way of using to figure out how old that sample is. It has a half-life of just over 5,700 years. We see some other examples here. Radium, this is the more common form of radium, the stuff that we find again in rocks. Uranium-238, common form of uranium. Again, we find it in rocks. We also can try to purify it and enrich it for other purposes, nuclear power, nuclear weapons. In the medicinal areas, so if you have any kind of radiological technique, either a spectroscopy technique, like where they use radioisotopes to help find goiters or ulcers or other kinds of internal issues. Some of those isotopes are found here. Nice thing about almost all of them, if you look at the half-lives for these, the half-lives of these are relatively short. That's a good thing. They're going to be used in medical imaging, or if you're going to have to ingest them, you don't want the radioisotopes hanging around in your body for a long period of time. So these half-lives being relatively short, it's a pretty good thing, actually. Okay, so what do we do with these? What kinds of calculations can we do? Well, the idea that we're going to run into pretty much every time here is we're going to have to do one of two things. We either have to figure out how many half-lives have happened, or we need to use that information to figure out how much sample is left. And sometimes in this problem, we have to do both. So in this problem, we are told the value of the half-life. The half-life is 38.1 years. If I want to know the number of half-lives, what I need to do is I need to divide the time that has elapsed divided by the half-life. So we are told that the time that elapsed is 152.4 years. We're also told that the half-life is 38.1 years. Do a quick calculation here. 152.4 divided by 38.1 would give me 4 half-lives. To answer the question, how much sample remains, we need to take the starting amount and divide it by 2 to the n, where n is the number of half-lives. So we started with 36 milligrams. We divide that by 2 to the 4th. Since there were 4 half-lives, 36 divided by 2 to the 4th would give us 2.25 milligrams remaining. So that's one way to do this calculation. Now, if this second equation here on the bottom kind of confused you, where you didn't like having to do the exponent and that kind of thing, that's okay. There's another way to do this. And the alternative way to do this is just to take that starting amount, 36 milligrams, and we're just going to divide it by 2 as many times as we have half-lives. So in a lot of ways, this kind of can be easier, at least to see. Okay, half of 36 is 18. Half of 18 is 9. Half of 9 is 4.5. Half of 4.5 is 2.25. I can count it. 1 half-life, 2, 3, 4. So I can literally just cut the sample in half that many times as well. And honestly, it doesn't bother me going either way. In fact, you'll often see if I'm doing a problem like this, sometimes I'll just sit there and do that a little bit with the arrows there. Okay, 36 is now 19, or 18, 18 is now 9. I won't even bother trying to, figure out what 2 to the 4th is. I mean, I know it's 16, but you can go either way with it. But these are the kinds of steps that you'd have to do for these calculations. Figure out how many half-lives there are. Use that to figure out how much sample is left. Now, if I'm given the opposite, I can use a similar ratio to try to figure out how many half-lives have gone. And if I know what the half-life is, that'll tell me how much time has gone by. If I know how much time went by and I know how many half-lives there are, then I can use that to figure out what the half-life is. So there's a lot of different kind of directions we can take these kinds of problems. They all fit in the same box though. Any questions with this? Okay. Let's see if we understand the concept then. Carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? Okay, slightly different kind of problem here. We haven't actually seen a half-life yet. But how much of the half-life have we seen? Have to be a little more precise than that. So if we're trying to figure out this fraction, we need to take the time that's elapsed divided by the half-life. So 2,000 years have elapsed. The half-life is 5730 years. So if I do the calculation there, we get 0.349. So 34.9% or 0.349. Sydney? Well, that's a very interesting question. What would you round it up to is the question. Okay. You could probably make that argument. You know, we haven't had a big discussion in this class about significant figures and what it means to, you know, how many digits do I carry out? I mean, you do the calculation in your calculator, it'll give you an infinite number of digits, or at least as many as fit on the screen. How do I know how many to carry? You know, we have sort of some ways to do it. Generally speaking, for a class like this, we tend to fall into rules of thumb. The rule of thumb we would use in this kind of case would be something more along the lines of how many digits went into the calculation, which would be 4. And so that's how many should come out of the calculation. That's kind of a general good rule of thumb we can use so that we know when to stop writing down the numbers and when we can round. So since we're not being too strict on that, if you put 0.35 in there, I wouldn't say anything about it. But, you know, there are technically rules that govern this, but we are technically ignoring most of them. Any other questions? Mackenzie? Right. So if it asks for fraction, then yes, decimal is how they want the answer. If they want a percentage, then they'd ask for a percentage. And so you'd have to multiply that by 100. All right, any other questions? All right, try this one for yourselves here. The half-life of iodine 123 is 13 hours. How much of a 64 milligram sample is left after 26 hours? Okay, so the first thing that we needed to do was we needed to figure out the number of half-lives. So 26 hours have elapsed. The half-life is 13. So I'm dealing with 2 half-lives. And so I need to turn that 64 after 2 half-lives. So after the first half-life, it's 32. After the second half-life, it's 16. All I'm doing is I'm just dividing by 2 each time. So 16 milligrams would have been the correct answer. Now you could have easily done the same thing. You could have gone, okay, 2 to the 2 is 4. 64 divided by 4 would give me the same 16 milligrams as well. Either way would work. It's a preference thing. All right, let's try another one. Which of the following radioisotopes are most likely to be used in nuclear medicine? We've got potassium 40, potassium 42, or iodine 131. Okay, I'm hearing B. Okay, Joel, you said B, right? Yeah. Okay, why B?
I mean, I think that's a relatively short half-life. I don't think you want to have any radio.
Yeah, pretty good reasoning. When it comes to radioactive substances and things like medical imaging, we're going to choose things that have relatively short half-lives, because since we are putting those materials in our bodies and they are going to emit radiation as they sit in your body, you don't want something that's going to be sitting around in your body for 1.3 billion years. So definitely B. Could we make an argument for C? Yeah, 8 days isn't that long. And depending upon what it is, what kind of stuff it emits, how much you're putting in your body in the first place. Yeah. So C is a reasonable one as well. And actually C is used. Radioactive iodine samples are often used to find things like thyroid cancer and throat cancer, since iodine collects on your thyroid gland.
If you have like multiple intake sessions, I guess, in a week, could you also make that argument? I don't know if that's a thing, like you have an appointment for imaging on Monday and you got another one on Wednesday, so you just
Probably not, because chances are these are ingestibles. So this isn't like just going and getting your x-ray taken. This is something like, if anyone's ever had like a GI taken, you got to drink a gallon of this junk that tastes terrible. And the reason you have to drink all that junk is because that's where the radioactive isotopes are getting their way into your gut, so that they can track it and all of that. Chances are pretty good that, unless we're looking at a really kind of unusual case, you're probably not going to have multiple sessions of that kind over the course of a week. Usually that kind of a diagnostic is something that is done almost in like a one-shot kind of thing. We do it once to try to find something, and we let it pass through you, because it is kind of invasive to have all of that radioactive stuff in you. So no, it's not, this isn't the same as, I'm going to, the doctor, or I'm getting an MRI taken several times over the course of several weeks. That's a different kind of imaging. That's not going to involve radioisotopes coming into you, like intentionally. Those kinds of radioactive things that you would get are from the machine itself. And so to that end, they would provide you with protection on your other organs that aren't being scanned if you had to go in multiple times over a course of a period of time. So no, this is different from like an MRI or your standard X-ray. This is usually this kind of imaging, PET scanning, CAT scanning, usually involve the injection or the ingestion of some kind of a radioactive material, something that they are going to say, here, take this. It's going to light up on the detector screen when we go to take you to the PET scan. All right, the last thing that we're going to get into is, kind of the thing that brings about the most apprehension when we talk about nuclear processes. We know about radiation. We know about, things that occur in the background. What we don't always really have a good handle on are these kinds of artificial processes that have led to major technological developments, but also major ethical decision-making dilemmas in terms of when is it appropriate to use this kind of technology. So the story comes about from the 1930s. In the 1930s, scientists discovered that if you bombard uranium-235 with neutrons, eventually one of those neutrons will stick and turn the uranium-235, which already has radioactive tendencies, into uranium-236. Uranium-236, in addition to being just plain old radioactive, is so freaking unstable that upon formation, it basically just rips itself in half. And the result of that ripping itself in half is we get a radioactive isotope of krypton, krypton-91, and a radioactive isotope of barium, barium-142. In addition to that, the lack of stability inside of that nucleus is so much so that in the process of ripping apart, 3 free neutrons shake loose from the tree as the whole process is happening. And what's interesting about those 3 neutrons is that they are coupled with a gigantic amount of energy as that unstable nucleus rips apart to form these more stable yet still radioactive nuclei. This process became known as nuclear fission. That's Fission, the first term there. And so all that this slide is saying is basically putting into words what that picture on the last slide was saying. That energy that came from the breaking apart of that nucleus becomes what we now call atomic energy or nuclear energy. And the other big consequence of that nuclear energy is found right here. Those neutrons that are ejected in the process have a ton of energy in them as well. Energy enough that they can mimic the process that caused this whole thing to happen in the first place. So now those neutrons can go out, they can hit on the other atoms of uranium-235 that are in the sample and cause them to react and form new fission products and even more neutrons. And you can see how this could become kind of a problem. Every time we get one of these splits to occur, the split generates 3 more neutrons that can cause 3 more atoms to split. And each one of those can cause 3 more neutrons to come out, and 3 more neutrons, and 3 more neutrons, and so on. And so what you have evolving very quickly in these kinds of processes are nuclear reactions that are going to generate a ton of energy very, very, very quickly. And so it became a matter of what do you do with all that energy? Well, in the 1930s, the primary aim of that project, this is the Manhattan Project, was to convert that energy, figure out if we could do it in the first place, but then use that energy to figure out how can we harness that into a powerful weapon that could potentially stop a war. Yeah, we had a little bit of help. In nuclear reaction terms, this is what has happened. A neutron comes into contact with the uranium-235. Together, they form the unstable uranium-236. That uranium-236 splits into the krypton-91, the barium-142, those 3 neutrons, and that bucket full of energy. The propagation of that nuclear reaction to form other nuclear reactions is what we call a chain reaction. And what's important to note is that for a chain reaction, requires what is called a critical mass of fissile material. Now, 2 terms embedded in that. Fissile material, that's just the uranium. That's the stuff that can break apart. Critical mass, that's the minimum amount of that fissile material that is necessary to cause a chain reaction. If we are below the threshold of a critical mass, then yes, one reaction can beget another one, but it is kind of controllable. It doesn't go out of control crazy and generate more energy than we can harness. And so if you want to know kind of the difference between what happens in a nuclear power plant when it's running appropriately and what happens in an atomic bomb, that is the difference. In the nuclear power plant, there should not be a critical mass of uranium inside of the reactor. Now, the key word there is when running correctly. If you think about some of the things that, some of the nuclear disasters that have taken place, that can be one of the ways that it goes wrong. In particular, we're thinking Chernobyl here, as opposed to some of the other ones that have taken place even in the more recent memory. Whereas atomic bomb, you've got well over the critical mass. And so this chain reaction takes place and all of these fissile uranium atoms start to rip apart around the same time. And all of that energy gets bundled and accumulates and accumulates and accumulates until boom. So if we look at the 2 atomic bombs that have been actually used in wartime purposes, you've got the Hiroshima bomb, which was using uranium. If you think about it, it's not that big. I think it's probably the most surprising thing when you think about it is, as far as like tip to tail, it's only about 9 feet. Now it weighed 9,000 pounds. So it was a very dense 9 feet. But it wasn't super big. Now, uranium-235 was the substance in there, and obviously they packed a ton of uranium-235 into that bomb. The one that fell on Nagasaki, the Fat Man, this one was a little bit larger and a little bit heavier. And what kind of made it stand out was it definitely was more protruded. It was rounder than the other one. The other thing was that instead of the uranium, they used plutonium. So that's nuclear fission. And like I said, nuclear fission has been around for a long time. You know, again, dating back to the 1930s, where we started trying to work on it, do it on purpose. And then after World War II, try to use that same technology to provide for us a very efficient form of electricity generation. And that's what nuclear power plants are. And while we haven't built any for non-military purposes in several decades, there are still roughly 90, 100 working nuclear power plants here in the United States. What was that? Yeah, they're responsible for about 20% of our power. Now, in military applications, it's actually a good bit higher, because if you're on a battleship in the middle of the Pacific Ocean, there aren't a whole lot of sources of stable electricity out there to run a small city, which is basically what a cruise destroyer is. Nuclear power is the only way to power that city. And so what you'll find inside of those ships at their very heart is there is a small scale light water reactor in there to power pretty much everything that the ship does. And so it's not solar dependent, it's not current or tidal dependent, it's not geothermally dependent or wind dependent, it is completely self-sustaining. Fusion, on the other hand, fusion is something that has been occurring in the universe since pretty much the dawn of time. Nuclear fusion is basically what happens inside of stars. And from those stars, we see the conversion of hydrogen into helium. And we also see the conversion of hydrogen and helium into other elements as well. Again, if you want to go back in the history of time, all of the elements that we have on the periodic table, at least all of the ones that are naturally occurring, started out in stars somewhere. It was fusion reactions that drove the formation of most of the elements, especially in the early days of the universe. Now, what happens in fusion reactions? We basically have the opposite of a fission reaction. Fission reaction started with something big and broke it apart into some things that were smaller. In a fusion reaction, we start with small things, and under high temperature and pressure, we force them together and they form a nucleus that is larger than what the two things were beforehand. So in stars, most commonly, in our star, the sun, what we are seeing primarily happening there is the fusion of hydrogen nuclei with each other. Those hydrogen nuclei can come in the form of, just hydrogen 1, or in a lot of cases, tritium and deuterium, the two other isotopes of hydrogen, where their fusion will create an atom of helium along with a neutron and a bunch of energy. Now, as human beings and as scientists, we've been trying to figure out ways to replicate these processes for quite some time now. Because after all, if we could figure out a way to do fusion, we wouldn't have to worry about the nuclear fallout and waste associated with fission. Problem is, there aren't too many vessels out there that can stand up to 100 million degrees Celsius in temperature. Those materials that we have would melt very, very, very quickly under those circumstances. There have been researchers that have tried to make up for that by increasing the pressure and lowering the temperature. None of them have been successful thus far. In fact, really, no one's come close. Some have claimed to come close and not actually had any verifiable proof that they did. So this is mostly confined to stars, but it does generate a ton of energy when it does. So let's make sure that we have our terms straight here. If a nucleus splits, is that fission or is that fusion? That's fission. If large amounts of energy are released, is that fission or fusion? It's both. Now, I think the book is probably making the argument that fusion releases more energy, but I don't think anybody here would argue against the fact that fission creates a ton of energy. Small nuclei form larger nuclei. That's a fusion thing. Hydrogen nuclei react. That's also a fusion thing. Several neutrons are released. That's a fission thing. Fusion does release neutrons, but it's usually like one. Keyword there is several. Okay, can we bring together the stuff that we talked about on Tuesday with this new information about fission and fusion? So if I have this nuclear reaction taking place, what would I expect my mystery particle to be? Well, we would handle this the exact same way that we did on Tuesday. What's my total mass number? 236. What's my total atomic number? 92. So if this is what I'm supposed to have on each side, what do I have right now? Say I have 137 from the tellurium. I have whatever this is, and I have 2 from the neutrons, because there are 2 neutrons. So 137 plus 2 is 139. 236 minus 139 would give me 97. Now on the bottom side, I've got 52 protons. I don't know how many for the mystery particle. No protons in the neutrons. So that's a total of 52. 92 minus 52 is 40. So my mystery particle has a mass number of 97, an atomic number of 40. And that's ZR zirconium. So this is pretty much the exact same thing that we did on Tuesday. We've just added a slight little wrinkle to it where we have multiple products, multiple reactants. We just have to make sure that we keep track of everything appropriately. All right, any questions? All right, so we have reached the end of the chapter, but as you can tell by the clock, we have not reached the end of the day. So that means it's practice time. So I've got a worksheet here. I'm gonna pass that out. Feel free to kind of work together. And with about 5 minutes left or so, we'll go through the answers together and we'll call it a week. Question?
Yeah, is this to help with
Yes. So it should help all around. It should help in the study module as well. Because basically the quiz and study module should